We began, some lessons ago, with Einstein looking at the smallest of scales, in 1902 to 1905, measuring the size of an atom or molecule, bouncing photons in his mind off of electrons on the surface of a piece of metal, looking at how an electron would scatter in an electric or magnetic field, and seeing how that process would change as one introduced the concerns of relativity. But now here we are in the midst of World War I, and in 1915 to 1916, Einstein has, after the hardest work of his life, created this new theory that related the geometry of the universe to the mass and energy in it. And those equations, the Einstein equations, he then says could be used to explore not just what happens with the bending of starlight around the sun, or what happens as light leaves a gravitational field or falls down into it, or the perihelion of Mercury as it precesses around the sun. All of these things are local tests, but now he says, let's imagine general relativity applied to the widest structure that we have, the universe as a whole. He says this in his first paper on cosmology in 1917. If we are concerned with the structure of the universe only on a large scale, our procedure will somewhat resemble that of the geodesists, who, by means of an ellipsoid, approximate the shape of the Earth's surface, which on a small scale is extremely complicated. Now, if we are trying to climb to the 29,000-foot peak of Mount Everest, or going down to the edge of the Dead Sea at 1,300 feet or so below sea level, the Earth appears enormously varied, but step back and it's almost a pure ellipsoid, a sphere spun and expanded slightly around its equator. And that's what Einstein wants to do to the universe as a whole. He says, don't worry about the changes in the space-time structure near the sun that makes the perihelion of Mercury move. Don't worry about how that distortions in space and time bend starlight around the sun, or change the frequency of light as it falls to Earth or rises from it. No, he says, let's imagine mass and energy spread out evenly over the universe and examine the geometry of the whole of our universe. The conclusion, Einstein says, that I shall arrive at is that the field equations of gravitation, which I have championed hereto, still need a slight modification. We need a generalizing modification of the field equations of gravitation. So what's wrong? What's this little blemish that he wants to fix? Well, Einstein believes deeply, as most everyone did, that the stars and galaxies around us are essentially fixed, apart from some small local motion. That the universe is a stable, static place. And so, realizing that gravity would crush the universe down and collapse it, he says there must be something to push it back out, a kind of anti-gravity that would stabilize the universe to reveal the static quality that he absolutely believes is there. That added bit of anti-gravity, that repulsive force that he introduced, comes into the equation, the symbol lambda, as what comes to be known as the cosmological constant, the outward pressure that compensates with gravity to fix things. Now, in the years after Einstein's general theory of relativity, around 1915, completed in the years 1915, 1916, quickly generalized to cover the universe as a whole in 1917, other people became fascinated by Einstein's idea about applying a new kind of science of the universe's structure. And one of the people who was following very closely what Einstein was doing was a young Russian physicist, Alexander Friedmann, who expanded on this idea in a paper in 1922 and then talked about it in the years afterwards. What Friedmann said was that Einstein's equations actually admitted of different solutions. You could make that cosmological constant have different values, and as you did, you were essentially changing the structure of the universe, the curvature of the universe, and whether it would expand or contract. there were actually a whole range of possible things that could happen in the universe, only one of which was stability. Very different from Einstein's interpretation. Einstein wanted to fix the universe. Friedman said all of these things are possible. The universe could expand forever, the universe could contract, or the universe could stay stable. He said the variable type of universe represents a great variety of cases. There can be cases of this type when the world's radius of curvature is constantly increasing in time. Cases are also possible when the radius of curvature changes periodically. The universe contracts into a point into nothing, and then again increases its radius up to a certain value, then again diminishes its radius of curvature, transforms itself into a point, etc. This brings to mind what Hindu mythology has to say about cycles of existence, and it also becomes possible to speak about the creation of the world from nothing. Well, Einstein hated Friedman's idea. He thought of it as a kind of mathematical trickery. The way he had thought Minkowski's invention of space-time was just mathematical fancy dancing. He wanted the physics, and he couldn't believe that the universe could admit such crazy things as collapse, expansion, or expansion and contraction in a cyclical way. But then, after blasting Friedman, about 8 months later, he wrote a letter, published it, conceding that Friedman's solutions were validly reasoned. He then wrote, by hand, to which a physical significance can hardly be ascribed. And then he crossed out those words, so they never occurred in his scientific apology to Friedman, essentially. It was good he did, because the universe can do all of those things. Those were valid solutions to the equations, and soon afterwards, a couple of years later, Edwin Hubble, an American astronomer, in 1929, started looking at the galaxies that could be measured and looking at their redshift as a measure of their speed of recession from our point of view. And what he found was really interesting. He noticed that the farther a galaxy was from us, the faster it was going away. Now that seems very strange, but actually we can understand it pretty clearly with a simple demonstration. A balloon universe. So here we have one, a balloon in which we are marking these stars or galaxies that are, one of them is, say, an inch away from Earth, and the other, say, 2 inches away from the Earth. If we blow up the distance so that the close galaxy goes from 1 inch to 2 inches, then the 2-inch galaxy will go to 4 inches. So in the same time that the close galaxy gains an inch, the other one gains 2 inches. If we had one that was 3 inches away and the balloon doubled in size, it would go to 6 inches, so it would gain 3 inches. So the distance would be proportional to the velocity of recession. So we can see here, now we've doubled the distance, say, and the close galaxy is now 2 inches, and the far galaxy is now, say, 4 inches away. So that's really all there is to it. If the universe is expanding constantly, then the amount of distance gained in the same time will be proportional just to the distance away. This idea that the universe was expanding was a real shock to people. One of the scientists who turned his attention to it and began to reason hard about what this meant for the structure of the universe was Georges Lemaitre, a Belgian priest who studied with Eddington in Cambridge and at Harvard and MIT, wrote in 1925 a paper called A Homogeneous Universe of Constant Mass and Growing Radius, Accounting for the Radial Velocity of Extragalactic Nebulae. So his idea, building on Einstein, as Friedman was, for instance, was that he would introduce a real expansion and a real beginning, what he called a primeval atom of the universe. In 1931, Lemaitre wrote, "If the world had begun with a simple quantum, the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have a sensible meaning when the original quantum had been divided into a sufficient number of quanta. The beginning of the world happened a little before the beginning of space and time." Because Lemaitre was a priest, many have assumed he was simply inscribing religion onto his science. In fact, his position was much more nuanced than that. Lemaitre said that the question if it was really a beginning, or rather a creation, something started from nothing, is a philosophical question which cannot be settled by physical or astronomical considerations. He said this much later, 1958. But all throughout his life, he tried to keep a sharp boundary between his work in science and his work as a priest. Lemaitre: as far as I can see, such a theory of the Big Bang remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. He may keep, for the bottom of space-time, the same attitude of mind he has been able to adopt for events occurring in non-singular places in space-time. For the believer, it removes any attempt at familiarity with God. It is consonant with the wording of Isaiah's speaking of a hidden God, hidden even in the very beginning of the universe. So, Friedman explored these different possibilities. Lemaitre thought that there really was a beginning, and that you could look at these possibilities as physical processes. You could have a negative or a positive curvature, or even a zero curvature, and then study as real physical possibilities that one of these held, and was to be determined which, in understanding the actual structure of the universe. These ideas of Lemaitre and Friedman and Einstein's deep ambivalence about the changing universe persisted into the period through the late 30s and World War II. And after World War II, a new way of looking at this came into being that really began to give some physical reality to these possibilities. Because with World War II, with the study of atomic weapons and the beginning of thinking about whether you could have thermonuclear weapons, you could actually have fusion, and we'll talk much more about this in the time to come, but studying the transformation of elements, the breaking of a nucleus like uranium or plutonium into pieces, or the combination of elements like hydrogen into helium, gave people like George Gamow, a very interesting polymathic thinker, an idea that you could actually use the early universe as a kind of cauldron, to see it as a place where the elements were combining from simple protons moving around, banging against one another, forming into larger and larger nuclei and the other elements, and that maybe you could see the remnants of that early synthesis of different elements in the universe as it existed today. In a letter to Niels Bohr in October of 1945, Gamow wrote, "It would be so nice if the end of the war would mean the return to the peaceful life as some 15 years ago. It looks to me more as the eve of a great deluge coming from the east, which is bound to engulf the free man on the earth. Sorry. It would be really so much nicer if one could begin to work again on pure science without the heavy clouds hanging in the air. That is what I am trying to do at present, studying the problem of the origin of elements at the early stages of the expanding universe. It means bringing together the relativistic formulae for expansion and the rates of thermonuclear and fission reactions." So he's trying to form a peaceful science of cosmogenesis using the new understanding of nuclear physics that arose in the late 30s and during the war work. And as he does, he's looking ahead at the Cold War and his fears of what that might bring. Lemaitre remembered his conversations with Einstein throughout the 1930s and this period, and once commented that Einstein had told him, "Your calculations are correct, but your physics is atrocious." But by 1935 or so, Einstein found Lemaitre's work to be of extraordinary importance, indeed a kind of guide thread for thinking about the creation of the universe. So where were we at the end of 1945, 46, 47? We had an expanding universe treated seriously, embedded in Einstein's theory of general relativity, abandoning this idea of a specially tuned cosmological constant that would keep things stable, exploring the possibilities of a physical process of nuclear synthesis in the early moments of the universe, and that could leave traces that would give evidence of the Big Bang.